Thank you for the introduction. I'm happy to present our paper on dropping standardized testing for admissions, differential variance and access, which is joint work with Nick Hilgarg, now at Berkeley and soon at Cornell, and Hannah Lee at Stanford, and I believe at least one of my co-authors is here today. So the debate about standardized tests is actually a very timely topic. In 2018, the University of Chicago was the first top research university in the country to drop the test score requirement for US applicants. And from 1957 to 2019, when Chicago actually took that decision, the university had required its applicants to take some form of a national level test. And more recently, University of California this time actually dropped the requirement that US applicants submit SAT scores and also announced that it has plans to ultimately design its own test. So independently of this decision, the COVID-19 pandemic created another trend of waiving the test score requirement in admissions. And until today, we know that hundreds of colleges and universities have stopped requiring SAT or SAT, at least temporarily. So the use of standardized tests is actually an open and difficult debate. And a common question is whether dropping tests will help expand access and equity or instead lead to the admission of less prepared students. So here I want to tell you a bit about the pros and cons in this debate. So far, test scores have, of course, played a very important role in admissions decisions. And in fact, their use started in the previous century with the good goals of rewarding academic merit, breaking social class barriers, and giving all students equal opportunities. So proponents of test scores actually claim that standardized tests will offer some systematic way of collecting information about applicants and have concerns that the bias we see in other application features, like the bias we see in recommendation letters or essays, is actually greater than the bias we see in test scores. But the most important concern that they actually have is that dropping the test will lead to a statistical discrimination type of effect. And to explain a little bit more what I mean by that, here is a sentence from a New York Times piece, which I think very nicely summarizes this intuitive concern. So the concern is actually that when we drop test scores, a capable student from a little known school will be more challenging to evaluate. And this will, as a result, benefit students from privileged and historically familiar to the university backgrounds. So to give you another example, and of course, this is a very hypothetical scenario, let's assume that until now, Stanford used to admit a lot of students from the Palo Alto high schools, but also some students with high test scores from less known high schools around the country. So then if Stanford drops test scores, then this might lead Stanford to admit more students from the Palo Alto area and less students from the less familiar places. So this was the side of the proponents of test scores. But on the other hand, dropping test scores might also help expand access and equity. So for example, we see that there are racial and socioeconomic gaps in test scores. And we also see that there are several barriers to testing for certain groups of students, both in terms of the test preparation, but also in terms of the access to the test. So, for example, we see that 8% of lower income students compared to 78% of high income students use a test preparation service. And another study has also found that for every 10 poor students who score college ready on this test, there are 5 other poor students who would score college ready, but who take none of these exams. And to connect back to the decision of UC that I told you earlier, it was interesting to see that for master's admissions this time, UC Berkeley saw an 82% increase in the number of underrepresented minority applicants that they applied to their master's program this year after they dropped the GRE requirement. But of course, like we need to remember that this effect might also be related to the COVID pandemic, so we cannot draw any conclusions. So motivated by these two competing claims, I just told you about the role of test scores. In this paper, we studied two key factors when thinking about those tests. So the first one is actually the test scores and other application features informativeness. And the second one is the potentially exclusive nature of tests, which means that some students might not be able to take the test, and especially students from disadvantaged backgrounds. And given this Bayesian theoretical framework that we will build, we ask, what effect would dropping test scores have on academic merit, diversity, and individual fairness of the admitted class? And as we will soon see in the talk, informativeness in the sense of the test scores and other application features variance really matters and has an ambiguous effect on disparity. So sometimes it may harm or otherwise benefit different groups of students. So we show that dropping test scores may sometimes lead to a less diverse, less academically qualified class, but if there are substantial barriers to testing, then dropping test scores might actually help us improve both academic merit and diversity. And in the paper, we have several results like theory results, simulations, and a short data application using data from the Texas Higher Education Opportunity Project. And today I'll talk about most of these results. Okay, so now that the motivation is hopefully clear, the rest of the talk will focus on the model and some simple intuition. Then I'll talk about our theory results and then briefly about the data application. So let's jump right into the model. We consider a single school with some limited capacity C, which gets applications from a continuum of students, and this continuum has like a mass normalized to 1. So there are two groups of students in the population, A and B, and as I will show you on the next slide, the two groups might differ in their size and other characteristics. So each student is actually characterized by a true skill level Q, which is drawn from some normal distribution with parameters mu and sigma that are known. And this distribution is common for both groups A and B, which practically means that the two groups of students are a priori identical in terms of this skill Q. But the problem here is that the school does not observe this true skill Q, but instead sees some noisy features theta k, which are the sum of this skill Q plus some Gaussian noise. And the parameters of this noise distribution epsilon might differ, like they might differ first across different features, but also across different groups. And the difference might be both in terms of the mean and the variance. So this noise epsilon is actually drawn independently for each feature, but you can see already that the features are correlated because of the dependence on Q. So a convention, and it's more of a convention rather than an assumption that we make in the paper, is that group B students face an informational disadvantage, as we will call it, because of this unequal precisions between the two groups. So what specifically we assume here is that the total precision for group A is higher than the total precision in the features of group B. So this was the side of the students, and now what about the school? So every applicant, the school will see these features that I told you, the group and the theta k features. And then the Bayesian school will use this information for its individual to compute their perceived skill estimate, which we'll call Q tilde. So then the school who wants to admit the students with the highest skill will simply admit the top mass C of students with the highest skill estimates from those estimates. So based on this very simple model I just described, we will look at 3 candidate policies, a policy with tests, which will be our baseline, then a policy without tests, and finally, I will very briefly mention affirmative action with and without tests. And to compare the performance of these policies, we look at 3 metrics: academic merit, which is the expected skill of admitted students, diversity level, which is the fraction of disadvantaged students in the admitted class, and finally, we have something called individual fairness. So specifically, we measure the individual fairness gap, which is the difference in admissions probability between 2 students of the same true skill Q, but different groups A and B. So ideally, we would like this gap to be 0, like to have no difference. But when, for example, this gap is positive, I will say that this indicates discrimination against group B. Okay, so given this theoretical framework, and before I tell you any of our results, I want to give you some simple intuition first. So remember what I told you about the school's estimation process, right? The school observes the group and some available features of the students, and then they use this information to estimate the skill of every single individual student. But to actually decide who to finally admit, the school needs to repeat this process for every single applicant and then sort them based on their skill estimates. So at an aggregate level, the school will get some perceived skill level distribution for every group G. And they will use this distribution to pick the best candidates. So let's now see how admitting according to this estimates will affect diversity. So as I told you, the school optimized for the academic merit of the admitted class. So what this naturally means is that it wants to admit the applicants with the highest perceived skill estimates from each group. So what happens here is that although we start from two identical skill distributions of true skill here, I hope you can see my pointer, and the school is Bayesian optimal, then our assumption here on the differential informativeness between the 2 groups leads to a lower variance in the aggregate distribution for group B. So the higher uncertainty we have in the features of group B students eventually leads to more conservative, let's say, estimates for their skill at an aggregate level. And in the picture, you see that this translates to a greater concentration around the mean for this pink distribution of B students. So this already tells us 2 important observations. First, even though we started from noise distributions with different means, the distributions of this Q tilde, the perceived skill level distribution, have the correct mean. So the mean here, mu, is actually the mean of the true skill level distribution. So the school manages to eliminate the bias in the mean. But now in terms of variance, we see that variance actually differs across the groups. So even though the school knows that the 2 groups here have the same distribution of true skill, then the school will fail to correct for the variance. So what does this practically mean? It means that when a selective school with capacity C comes and sets an admission threshold here to admit the students with the highest perceived skill level, more students from group A here will be considered to be high skilled, and as a result, they will be admitted to the school at a high rate. So this is a point where this assumption here that C is more than 1/2 is important, because it actually implies that we are on the right tail of this normal distribution. So very simply, and I think it already becomes clear from the picture, group A students will be admitted at a greater rate than group B students. And this means that we have an underrepresentation of B students at the school. And here is another more general picture that I will use to convince you about some other properties. So on the vertical axis here, we have the true skill Q of a student. And on the horizontal axis, we have the perceived skill estimate Q tilde of the same student. And with a solid black line here, I will represent the admission threshold, and with a gray area here, the admitted class. And finally, green means group A and pink means group B. So similar to the intuition I just told you in the previous slide, we can again observe here that because of this differential informativeness assumption, the skill estimates of this pink group, the B group, is actually more regularized towards the mean. But actually with this picture, we can see more than that. So for example, we want to look at the individual fairness gap, right? So in the paper, we show that very high skilled students in group B have lower admission probability. And in the picture, we can see easily why. So suppose that we take all students with some high value of true skill Q here. So then if we look at the plot and the admitted students in the gray area, we see that the greater mass of green students, so the green group here, is admitted compared to this pink group here. But now if we take some students with some low value of Q, so if we are somewhere here in the picture, then this gap will become negative. And what it practically means is that low skill students from group B have some very low, as you see here, but still higher probability of admission compared to students of group A and the same skill. So this was for individual fairness. So now can we say anything about academic merit? And it turns out that in terms of academic merit, something more counterintuitive happens. So not only group B will be admitted at a lower rate than group A, but actually the targeting of high skilled students from group B will be worse. And again, we can see the intuition in the picture. So if we focus in this gray area of admitted students again, and just like move along this admission threshold, we can see that group B students here, the pink group, is relatively uniformly admitted across the spectrum of different true skills. But if we look now at the green group, we see that the school successfully identifies these high skilled students here. So it correctly admits more students from the green group. Okay, so now that I have hopefully given you some intuition, we can use this intuition to look at our main question, which is what happens when we drop test scores, and how does a test-free policy compare to a test-based baseline? And for simplicity, I'm going to assume that this feature K, the last feature, is a test score. So P-free will mean a test-free policy and P-full a test-based policy. And our first theorem here utilizes this intuition, I just told you. And to summarize, it says that under a test-based policy, disadvantaged students will be underrepresented. So diversity will be low. In terms of individual fairness, we find that very high skilled students in group B will have lower admission probability than same skilled peers in A. And in terms of academic merit, we show that the targeting of disadvantaged students is actually much worse. So now coming to the main result here, what happens if we drop test scores? So in that case, we see that, like in contrast to the previous test-based policy, the diversity level might decrease. The individual fairness gap might increase for high-skilled students, which is bad. But the actual direction of this change depends a lot on the informational environment we're in, and I will explain what I mean on the next slide. But in any case, we have bad news for academic merit. So the academic merit will decrease for both groups. And this is kind of expected, right? Because we remove a source of information, which is a test. So now to get some intuition about the informational environment that I just told you, we can look at diversity after dropping test scores. So as we show in the paper, diversity will improve after dropping the test, if and only if this condition I have here holds. But this condition is actually equivalent to this more intuitive relation here. So what does this inequality simply say? It says that diversity will improve if and only if the relative informational disadvantage of group B decreases. So actually, if the informational disadvantage of group B students decreases so much that it changes direction, diversity will not only increase, but the group B now will no longer be underrepresented. So the question one might ask here is this really a realistic scenario? And I think it's probably not. So if we go back to this New York Times piece I told you in the beginning, if we believe that the informational disadvantage persists after we drop test scores, then removing this test will actually harm those disadvantaged students. So the test in that case is still like a noisy but helpful source of information for those disadvantaged students if the other application features like, as I said, recommendation and says are even noisier for them. But there is something missing in this argument. So until this slide, I haven't told you anything about the second factor I promised, and this is access barriers to testing. So a twist here is that what happens when on top of the informational disadvantage that these group B students have, we also assume that students might face some barriers to testing. So practically, this means that there is only a fraction gamma G of group G that has access to the test. So now we can look again at the previous results I told you, but when we assume that group A students have greater access to the test than group B students. And an important feature here is that without a test, students cannot apply to the school with a test requirement, even if they're qualified. So a first question we can ask in this framework, which is very simple, is what happens when groups have similar information but face different levels of barriers? And the answer is simple, like fewer group B students will apply, so fewer will be admitted. But in the real world, things are more complicated, right? Groups may differ in their barriers, but they also differ in their informativeness of their features. So how can we choose between a test-free world and a test-based world? And the second main result of the paper says that the answer actually depends a lot on the actual level of access and the other parameters of the model. So what we specifically saw is that the academic merit of a group G will improve after we drop the test scores if and only if this group G has sufficient barriers. So actually it means that there is some threshold gamma hat G that we characterize in the paper so that the academic merit and similarly diversity will improve if and only if this fraction gamma G of students who can take the test is at most gamma hat G. So I think this result helps us understand a bit better the trade-off between informativeness and barriers. So a big concern that proponents of test scores had is that dropping the test would lead to less academically qualified students, right? And indeed, this is true. Like if you remember a few slides earlier, we showed that this would be true if all students had full equal access to the test. But now what the result on this slide is telling us is that this may no longer be true if there are substantial barriers to testing. So if we remove those high barriers and let more applicants apply, then we can potentially improve the academic merit of the admitted class. So a question is, again, can we benefit both groups by this change? And I feel like the statement actually shows is that the answer is maybe, but it actually depends a lot on the magnitude of the barriers that each group has and the test score informativeness per group. Okay, so before I move to the data part, I want to briefly mention affirmative action. So one natural question is, okay, like maybe we can apply affirmative action, which means that we can set a target level of diversity, a target fraction of group B students to admit, and then see what happens with and without tests. And
about 5-minute warning.
Okay, thank you. So what happens here is that if the results are mixed, so diversity will improve by definition, and the individual fairness gap will indeed improve for all skills of students. But in terms of academic merit, we might see that the gap between the two groups increases. And again, the decision to drop tests or not depends on the access level of a group, so the result is very similar to the previous case. So finally, moving to the last part of the talk, we use some data from UT Austin and the period from 92 to 97. We have several features like high school class rank, standardized test scores, demographic features, high school features like the economic privilege index of the school, admissions and enrollment decisions at UT Austin, and then transcript data of the students, of the enrolled students. So a problem we had here is that we cannot actually see the transcript data of the students who didn't enroll at the school. So instead of admissions, we actually simulate a setting where freshmen need to be selected for an honors program or a fellowship or a college transfer, this type of applications. And what we will do in the simulation is that for each individual student, we will use their final GPA as their true skill, and then features like class rank, college, or test scores as additional features. And to define the privileged and disadvantaged students, we will use the high school's economic privilege index. So based on this data, we will train two models using OLS and then sample an equal number of students from each group. And an important assumption that we have made here is that 2/3 of the disadvantaged group have access to the test, but it's not based on data. We didn't have this type of data. So at the high level, our experiments show that the answer to whether we need to drop the test or not depends again on the informativeness environment. So in our first simulation, we had the low informativeness case, which included the class rank, college, and potentially test scores. And what we find again is that dropping test scores will decrease diversity. And this is because the high school rank, which is basically our feature here, is very uninformative for the disadvantaged group compared to the test scores of that group. But now in our second simulation, where we use an additional feature, and this feature is the first semester GPA. So when we use a feature that is very informative for both groups, then we have the opposite effect. So after we drop test scores, diversity will increase, and academic merit, which we'll measure by the final GPA of the students, will slightly improve, as you see here. So I don't have time to spend more on here, but you can find the details in the paper. So moving towards the conclusion, I just want to mention that our paper contributes to a very long line of literature in economics and fair machine learning. And our model is actually an extension of Phelps' statistical discrimination model, but now with multiple features, non-identical distributions, and a continuum of candidates. And today I focused a lot on college admissions as our main example, but we believe that this is actually a very simple and general framework that we could use to model several decision-making problems. But of course, it still remains a very stylized model with several limitations. For example, we assume normal distributions, and the reason is to highlight the role of variance. we also assume a very specific notion of fairness. So in any case, I want to emphasize that we need access to more data to actually understand the barriers students face and the effect of different policies in admissions. So to conclude, I would like to reiterate the main message of the paper. So specifically, we find that the test scores and other features variance really matters and has an ambiguous impact on disparities. So dropping test scores may lead to a less diverse, less academically qualified class. But if there are substantial barriers to testing, then dropping test scores can indeed improve both academic merit and diversity. So thank you for your attention. I would be happy to answer any questions.